Welcome back to the workshop. We want to take a look at our last video, our last topic for section 4.2, paths and circuits. Now, we want to start off with a theorem that probably should have been included in our last video, which discusses Euler circuits. And the theorem simply states that a graph or a multigraph will have an Euler circuit if it's, well, first of all, it has to be connected. So suppose we have a connected multigraph to start with. But then that multigraph will have an Euler circuit if and only if all vertices are of even degree. So if you have a connected graph and you go through and you count or you determine the degree of each vertex, if they're all of even degree, then it does in fact have an Euler circuit. Furthermore, we'll actually have an Euler path if and only if all of them are even except for two which are odd. And of course, you, like our previous example, connect those two odd vertices to give an additional edge on each, which gives even degree on all vertices, and an Euler circuit can be found. Remove that edge to give an Euler path. Okay, so that's the first thing that we have. From there, we move on to a new idea, a different mathematician's paths and circuits. So let's take a look at those. Of course, first given here is that theorem that I spoke of. Feel free to read that. All right, so moving on though to our next collection of paths and circuits. In a graph, a Hamiltonian path is a path that contains each vertex once and only once, or exactly once, okay? So an Euler path is one which contains every edge exactly once. A Hamiltonian path is a path that contains each vertex exactly once. So they are different from one another most of the time. Very rare instances they're the same. All right, so each vertex exactly once. And then of course a Hamiltonian cycle is a cycle that includes each vertex once. And here it would be a cycle instead of a circuit, because if we're containing each vertex exactly once, then we certainly cannot repeat an edge either. So a cycle does not repeat edges or vertices. A circuit can repeat whatever you like, okay? So let's take a look at two examples. In the first one, let's find a Hamiltonian path in this graph. And then we want to decide if a Hamiltonian cycle exists. So it doesn't specify where we have to start or where we have to end. So I'm going to go ahead and just choose to start at R, and it's saying that a Hamiltonian path does exist, so I can confidently try to find one. And we don't have an algorithm for helping us in this case. It's simply trial and error. So let's give it a try. So I'm going to travel from R to S, and then from S to T. And here I have some options. If I were to, for example, travel along U to V, then I've got two options again. Oh, and oh yeah, no, this looks good. I know somewhere I've got a graph that's mislabeled as having the same vertex twice. We'll worry about that later when we come across it. So anyway, I travel along this edge from T to V, and if I do that, then I can travel on to X. And if I travel on to X, I'll never be able to get back to U, because even if I were to, even if I were to go around and try to go back to U, when I'm looking at a Hamiltonian path, I cannot repeat a vertex. So if I go to V here, I can't go back to U, okay? And if once I go to V, if I go to X, I can't go back to U. And if I were to say, all right, let's go to U, then I have nowhere else to go and I can't get to these vertices. So I find that I cannot go to V here. All right, that means I have to go to U if I'm gonna make this work. Still not even guaranteed that this is gonna work out, but we'll give it a shot. So from here, I've only got one place to go, and that's this vertex. Once I get to V, I have options again. And really here, either way would be fine. If we go to W, we find that we can travel to X, then to Y, then to Z, and we have gone everywhere. We have visited every vertex. So R to S to T to U to V to W to X to Y and ending at Z is a Hamiltonian cycle. Excellent. Oh, sorry. Nope, I lied. That's a Hamiltonian path. And we want to see if a Hamiltonian cycle exists. All right, so does a Hamiltonian cycle exist? Well, essentially what happens is as soon as I pass through V, I cannot go back to where I started. So if I started down here, go through V, I cannot get back down because I'd have to travel through V twice. So no, essentially V, right? If we removed V, we would actually have a disconnected graph. So once I've used it and I can't travel through it again, I can't get back to the top or back to the bottom wherever I had started. So no, we would have to pass through V twice, and then it would no longer be Hamiltonian. Okay. There's possibly, maybe, not even guaranteed a way that we could do this, passing through V. So what I'm saying is you might be able to identify something else as what prevents us from being able to create a Hamiltonian cycle. In this case, I'm saying V is something easy to pick out. If you picked out a different problem that prevented a Hamiltonian cycle, that's fine too. No worries. Our justifications might be different because there might be many reasons why we can't find a Hamiltonian cycle. We may find that they're pretty much the same thing, but that's fine. Whatever justification you have, no big deal. Just make sure that you can find your response and then justify it. In this case, no, Hamiltonian cycle exists. And I'm saying because we'd have to pass through V twice. All right. It's not a very rigorous explanation, but it's sufficient for now. All right, and this is the graph where I have this the same label given to two vertices. So I'm going to change this to black. It looks like I meant to have a W in here somewhere. So let's change this to a W. V was repeated, so let's change that to a W. All right, so we want to find a Hamiltonian cycle in this graph. So we're saying that there is a Hamiltonian cycle. We just need to find it. All right. Of course, you might run into problems. It's a trial and error sort of thing. So I'll share what I was able to find. So I start at S arbitrarily, travel to Q, and then travel to V. And once I'm here, right, I know that I want to end up at T, so I need to have somewhere to get. So I can say, all right, if I go up here, will I still be able to get back here? Yes. If I would have gone to R, for example, I would never be able to get to T now unless I went to T first. Okay, so I go to T, but then the only place to go from there is back to S, and we don't have all of the vertices included. So that doesn't work, okay? So we say to ourselves, we can't go to R because that's going to close our cycle too quickly. So we travel to V. We only have one option from V. We go to W. We only have one option. We go to U. We only have one option. We go to Y. Okay, so for the most part, so far, it's been pretty simple to find. If I were to go along this edge, of course, that would take me back to S, and it would end the cycle too early because we're still missing several vertices. So we go the other way to Z. Only one place to go, to X. only one place to go, to R. We've already visited Q, so there's only one place to go. And then once we're here, we can close and we're all set. So this is a relatively simple example, but it's the same idea in terms of what you're going to need to do when you are doing these for yourself. So which way did I go here? All right, well, I started at S, then went to Q, S, Q, then V, W, then to U, then to Y, then to Z, from Z to X, then from X to R, from R to T, and then from T back to S. This is a Hamiltonian cycle. Excellent. And that's all that the example asked for. So to finish off, we give a nice theorem that says when a Hamiltonian cycle will exist, which turns out to be maybe not the most fantastic, theorem ever, but it does tell us when one should exist. It will guarantee an existence. So suppose G is a graph with n vertices where there's more than 2 vertices. If for each pair of non-adjacent vertices, so non-adjacent, if for each pair of non-adjacent vertices, so Q and V are adjacent, so I could consider Q and T, Q and U, Q and W, QY, QZ, and QX, but not QS, QV, QT, or QR. Oh, sorry, QT if we can, not QS, QV, or QR. So non-adjacent vertices. If we have that the degree of U plus the degree, oh, that's not the notation we use here, the degree of U plus the degree of V, if the sum of the degrees of the vertices is greater than or equal to n, then it will certainly have a Hamiltonian cycle. Is this a necessary condition? It's sufficient. If we have this, yes, it will have a Hamiltonian cycle. But is it necessary? No. For example, I could have just simply 4 vertices, all connected like this. Hamiltonian cycle, bam, right there, that's it. But the degree of the non-adjacent vertices, oh, that actually works out. We would need to go 1 higher. There we go, up to 5. 5 vertices, but the sum of the degrees is only 4, which is less than n. Okay, so it's not necessary, but it is sufficient. All right, so that is Hamiltonian paths and Hamiltonian cycles. That's it for section 4.2, paths and circuits. So I'll see you guys back in the workshop a little bit later for section 4.3. You guys have a good one.